I'm John Coleman from the University of Oxford. I'm a phonetician. I'm sort of the linguist on the team. We've been working together. With colleagues from various institutions for a number of years on the problems that we're going to be telling you about today. Essentially modeling, seeing how we can apply various statistical techniques to model variation in spoken language with a particular goal, not that we're going to be dwelling too much on this today, of trying to better model sound change and historical evolution or historical changes in spoken language. Yeah, so this is the structure of the talk. As was said, all four of us are going to be talking, so I'll talk a little bit about the background, the historical linguistic motivation for the particular application we're going to be talking about today. And in particular, since we're going to be working on the analysis of spoken sound recordings of words in various languages, I'll pass on to Pantelis, who's going to talk a bit more about the modeling the acoustic dimension, and then we'll proceed to look then at statistical analyses that I'll leave to my more learned colleagues later. So historical linguistics is the area of linguistics that looks at the evolution of languages. And by evolution, I'm not referring to evolution on a sort of biological timescale, that is how human beings came to develop the faculty of language, but really by analogy with biological evolution, how languages have come to change over time, how languages that we know are from the past have come to evolve in sometimes in very well documented, historically well documented ways to languages spoken of the present. In that process of of growth, as it were, or change from ancient languages of the past to modern languages of the present day, we often see diversification and separation and differentiation of one modern language from another, which gives rise to the family tree model of linguistic evolution, which actually historically evolved at more or less the same time as the phylogenetic conception of biological evolution. It's the same. The metaphors have a common spring from a common origin, as it were. But the timescales we're looking at are much more recent, and we're looking at the evolution, as it were, of a cultural phenomenon, spoken language, over a period of, well, on the diagram here is of a diagram of the branches of the Indo-European family tree, most of the languages of Western Europe and also South Asia. And the root of the tree here is the reconstructed, the hypothesized ancestor of all of the modern Indo-European languages, Proto-Indo-European, that's dated to about 6,000 to 8,000 years ago. There's a lot of indeterminacy. Further up the tree, we can see that there are clusters of the tree, the various branches of the Indo-European language and language family. And today we're going to be talking about some data from the Romance language, the Romance branch of Indo-European. These are languages: French, Spanish, a couple of varieties of Spanish, Italian, Portuguese, and a few others that we're not going to be talking about, Romanian, for instance, and one or two others, that we know as a historical fact have evolved from a common ancestor in Latin. For many of the languages see on the tree here, the Indo-European languages, they do have fairly well documented textual evidence from the past, which is why our hypotheses about the nature of the evolution of these languages in historical terms is rather detailed and fairly reliable, and many of the languages continue to be spoken, albeit in changed form, to this day. Our interest in historical linguistics we're not alone in that interest, of course. There are people looking at evolution of language from other disciplinary perspectives as well. So I'm a linguist, you're statisticians, but there are colleagues in other fields, anthropology, genetics, sociology, and so on, who are also interested in process of evolution more generally, and sometimes more specifically in the process of the evolution of language. In the past, so the past 200 years of scholarship in linguistics and comparative philology on the evolution of language has tended to, well, has always really today been based upon the analysis of textual evidence, written records, of necessity. Most of the the ancestral, the archaic evidence only comes down to us in the form of texts. And text is just one kind of representation of language, and it's a rather unusual and particular sort of representation. It's only found we only have text in some cultures. And texts, in whatever writing system they use, they're very fixed, very static, very invariant. There may be variations in handwriting or graphic style, but by and large, the texts give a representation of language in terms of discrete units that are very fixed and remain fixed from one generation or from one century to another, and they don't display the variation. Whereas when we look at living languages, as you know, from our present-day perspective, with the tools of acoustic analysis and so on that we have, it's immediately obvious that there is massive variation in language wherever you look when we look at spoken language. For linguists, spoken language is the real deal. That's the primary data, really, and the textual representations are only a sort of pale and rather fossilized reflection of that. So the sort of overarching goal of the research, only part of which we're talking today here, the goal of our group is to try to understand better and model better how language change and evolution takes place when we look at using spoken recordings. We don't have spoken recordings for earlier stages of languages because sound recording has only existed for 100 years ago. So therefore we have to estimate, guess, model, create synthetic simulations of how languages may have sounded in the past, and that involves the development of novel statistical and computational approaches in order to try to, reconstruct the sounds of languages from the past and also understand how we got from how it was spoken in the past to how languages are spoken today. What we see today in the recordings of spoken languages is variation, differentiation between different languages. So we're going to be focusing on the diagram's gone. We're going to be looking at a number of Romance languages today, in which the words may be similar to one another. Words of similar meaning are similar to one another, but there is some variation. Because of the similarity, we can guess at some features of what the common underlying ancestor of those words were. In fact, we have Latin to check against, but we can make good guesses about the ancestor. So the 5 varieties that we are going to look at are words from Portuguese, French, Italian, Spanish. In fact, the recordings we collected for the purpose of the data set that we're going to be talking about in today's modeling work we found, could you go stick previous slide, please. The data we had contains, I collected a certain amount of recordings of spoken digits, the words meaning 1 to 10 in these varieties, and the recordings that we had available included a lot of examples from Spanish as spoken in the Americas, which are a little bit different in their pronunciation than in Iberian Spanish. In fact, within any of these languages, there's a lot of variation in pronunciation that isn't shown in the normal written representation of the words. Neither is that variation really shown in the phonetic transcriptions that are given here, which which try to capture the details of the pronunciation and to show the pronunciation differences between, these are different forms of the word for one in the various languages. You can see that they textually look different, whether you're looking at the normal orthography or the phonetic transcription. But even the phonetic transcription in this case is still a textual representation. It doesn't reveal doesn't show the structure of the variation between these languages, and nor does it say anything about the variation within each of the languages and the variation in the population of speakers and the multiple occasions on which people use these words. So in the spoken records and the recordings that we have, there is a much richer kind of acoustic variation that we would like to be able to use to model. So the focus of today's work really is trying to understand better how we can model the variation between languages that are historically related. We look at the structure of the space of acoustic variation. Now, in trying to model the structure of the variation across the different spoken forms of a given word within a language or across a group of related languages, we would like to be able to sort of move continuously from one pronunciation to another, to be able to, for instance, to be able to calculate what would be an average pronunciation of several pronunciations, in order to determine what is common to the various pronunciations. Or we might be able to, we want to ask, how do you move? That is, how do you sort of interpolate from one pronunciation to another to understand what's the shape of the nature of the space as you move from one recording or one pronunciation to another. Now, it becomes immediately obvious that we can't do those sorts of computations or calculations just using the raw signal. The time series, the vector of the sound that's recorded when you record, say, the voltage on a microphone is a rapidly changing time series, and so the recordings are easy enough to obtain, but it's not possible to move from one sound to another in a strictly linear way using representations such as signal representations. To illustrate that, could you click on the far right hand word, please? This is the French word un. Not hearing anything. That's the French word un. While he's sorting that out, I'll just refer to the word on the left, which is the Portuguese word for one, which is pronounced something more like So there are some respects in which they're similar. They're both more or less just a nasal vowel, but a different kind of quality of nasal vowel. And here we go, speakers. If we take the recordings of each of those words, an token and an token, and simply add the two time series together, divide by 2 to obtain a mean signal, what we don't get is a word in between these two pronunciations. Let's move on. I will play that. But I'll explain verbally. What you have, if you compute that mean, is in fact just a mix of the two sounds. It's just like hearing the two sounds, the two original sounds, and simultaneously, as if the two original recordings spoken by two speakers were just both here in front of you. So it's just a mix of the two of them at half the volume. It's not a mean in the sense of a pronunciation which is halfway between one and the other, which is what we would like to have. So I'm going to pass over now to Pantelis, who's going to say a little bit more about the audio data, the data set, and how we processed it for the experiments that we're going to describe.
So the main problem I was presented was that, in essence, you cannot use the raw waveform in order to just average it or take some kind of linear transformation of it and get it out. What we want to go forward with is something more expressive, something that we can go ahead and use in order to model all the aspects of an utterance. That would be the spectrogram. So this is the basic idea, and we will say exactly what we'll decompose it afterwards. That we're able to go ahead from a waveform that we have, that is modeling a spoken word. Go ahead, have the log spectrogram of it. So effectively, a series of continuous Fourier transformations, and then that therefore encapsulating all across time all of the frequencies that are spoken, and then using the amplitude of the Fourier transformation, go ahead, smooth it, and align it and smooth it, and therefore we have what we call now the fundamental unit of analysis of this work, which is now these surfaces. This is a basic presentation of what's going on. So, unfortunately, there's no pointer. What I want to say is that while the right hand on the left hand side, the waveform is only on time, and we have some amplitude differences. What you're looking for, we are moving towards a surface that is across time. So, if you like, under the arch, all that the arch is extending time. We're able to do a small Fourier transformation and then keep moving that window, therefore going forward and reconciling the spectrogram. The window in this case is Gaussian, and because of the sampling rate, this is specific to the sample, we end up with 160 samples per utterance. And okay, and that was the spectrogram, and particularly we're working with this spectrogram has the phase information has a amplitude and phase. It's important to note that we're working only with amplitude, and we do know that certain information will be lost for that reason. Phase will not be accounted for. And then we use with log 10. This is something effectively working with decibels. Right. Now, as you saw the previous slide, the spectrograms were not smooth. We needed to make sure that they correspond to a smooth function in the sense that they have at least second derivatives. And there are many ways of smoothing. The one that we chose for this particular application is working with is based on a representation based on a base, that is the discrete cosine transformation. This is what Garcia is doing in that paper. Especially the JPEG. This is what JPEGs are doing, and similarly. And that was the smoothing part. Importantly, after smoothing, we realized that everybody knows that people have different tempos when they're speaking. And alignment of the functional data is something important because difference in amplitude should be difference in amplitude rather than difference in actually the time evolution of the process that we're looking at. Here, I would draw the attention to the fact that this is a monodimensional smoothing, despite the fact that, registration, despite the fact that we have what you saw as surface, we're interested in aligning only across time, not across phases. Not across frequencies, sorry. If we do that, there are techniques that usually they're 2D and they will try to align both phase and frequency at the same time. Time and frequency at the same, synchronously. And that would be wrong in this case. So we're using, in this case, we generalized a well-defined alignment process by Tang and Muller, which is effectively like a spline. We have what is called a warping function, that's G, and that warping function is mapping the evolution of time between of a process against a universal time, if you like, of evolution. So now that the data are aligned and smooth, this is what you're going to use that sigma there, S, that represents a two-dimensional smooth and aligned spectrogram. And now we have the working hypothesis that while every speaker has a particular spectrogram associated with them, what happens is that when they speak a particular word, there is underlying structure that is particular to the language. So in that sense, this is the underlying structure we want to work with. We don't care about the speaker variation, we don't care about the actual language, like the word variation, like the content 1, 2, whatever. So this is more formally, therefore, there is this the spectrum that we have smooth. It can be decomposed likely under that mean variation that the mean component that I mentioned, which is particular to the language, L, and I corresponds to the digits that we're looking at, plus some variation that is due, like epsilon there, that is due to a specific speaker saying a specific word, a specific language. And that, okay, it's assumed to be IID, zero mean and everything. The important bit here is to begin with is that now that epsilon has a four-dimensional covariance, exactly because it's a covariance between two-dimensional objects. Each of them theoretically has its own frequency and time dynamics, and therefore we have this at the end, this covariance, language-specific covariance, has four components: omega 1, omega 2, referring to frequencies, T1, T2, referring to times. Now, taking a step back, if we have if we assume that there is a mean component, we can, for particular to language and a word, we can remove that. We can go ahead and subtract that from the spectrum that we have, and therefore what we have is what we call like a residual spectrogram, and that is not particular to it's particular language, but it's not particular to a speaker, neither a specific utterance. Therefore, now what we can have these are residual spectrograms that are, if you like, realizations of the covariance that we mentioned before, that they were specific to languages. And in total, exactly because we had 223 speakers and with 10 utterances each, so we're having 230 instances, samples. As you understand, this is not a huge sample. Therefore, we need to go ahead and find some ways of making our life easier. Like, you have to pick. Either you have an easier problem, bigger data, or better technique, if you like. But by far the easiest one is actually getting an easier problem for yourself. Therefore, we are having this separable approximation. We assume that we're able to marginalize across time and get frequency, covariances and frequencies, and similarly across frequencies and have covariance and time. This is an approximation that is not completely insane. It is, in a way, kind of like having a reduced rank approximation. And this probability assumption, there is a separate paper by John Aston and Pigoli and Pigoli that explores whether or not this is an assumption that is reasonable. We do know that linguistically this is not a limiting assumption, so therefore it's not by any means hindering our final goals. And the table below shows when they did separability tests in different with different combinations of fidelity, if you like, in the original assumptions. Now, exactly because this factorization is a product, like a factor, you can always, as any product, like you can multiply something a higher number and the other one gets smaller. A way of, and we need, so therefore is like defined up to a constant in a way. Therefore, a way of going forward was this dividing by the trace of it. I mean, you can have different things, like you can fix the trace itself. There was just one way. Yeah, pretty much this is the final thing, that after this we're able to go ahead and estimate particular covariances. These are for frequency, so you can see, for instance, immediately certain differences. So French and Portuguese. So Portuguese is the leftmost surface that you see, and the upper right corner of the French have certain variance on the end of the utterance. While the other ones don't have such a strong variance there. And with that, now it's came, like, while I say this, that, you know, it seems that Portuguese have more variance, the point is it that, you know, this difference is significant? And therefore, one of my co-authors will come over and say if that is significant.
We have already introduced a few assumptions in this model, but from the linguistic point of view, the most fundamental is the fact that the covariance structure is a property of a language and does not change between words, while the mean is word specific. And so now I'm talking a bit about how we checked this, the validity of these assumptions in our case. So to do that, I'll take a step back and start from a simpler scenario. So let's say that we have two samples of functional data, so classical univariate functional data, and you want to test if this has the same mean and covariance operators. There are many ways in the literature to test this assumption, this hypothesis. The one I'm going to introduce, because it's easy to generalize to our more complicated setting, is one based on a permutation test. So essentially what you're saying is if these curves have the same mean and covariance, under the null hypothesis they are exchangeable, so you can set up a permutation test as long as you have a test statistics which can measure the difference between the covariance operators between the two groups. And for a moment, I just denote this as the distance d there. I'm going to talk in a moment which kind of distance we may want to use. Okay, so once you have that, you can simply permute the labels between the two samples, compute a version of the test statistics on the permuted data set, and compute the p-value as the proportion of the permuted test statistics that are larger than the one in the original data set. This is a classical strategy permutation test. The only key point is choose in a intelligent way the distance between the two sample covariance operators. Now we did some previous work on this problem in the two sample cases, and essentially there are two different families of distance that you can use. One, you can say, okay, I'll simply ignore the geometry of the space of covariance operators. I will treat that as simply as a symmetric operator. You can say infinite equivalent of the symmetric matrices, and I'm using linear distances there. That's a valid strategy. However, we have seen that using a distance that takes into account the nonlinear geometry of a space, and when I say nonlinear geometry, I mean, for example, the constraints on the eigenvalues, the positivity, etc., or non-negativity in this case. This leads to better results, essentially, better power, a larger power for the test. So for this reason, we introduced these distances. So for example, the square root distance use a simple strategy, which is mapping the operators into the space of symmetric operators using the square root transformation, and then in that new space you can use the linear metric. Or the Procrustes distance is an improvement on that, because essentially it takes into account the fact that in this mapped space you have an arbitrarity given by the all possible unitary transformation U that can be applied to the symmetric operator and do not really affect how the original covariance operators. So the Procrustes distance, the way I see that is a way to get rid of this arbitrariness by minimizing overall possible unitary operators. Okay, so this is a technicality, but the main message is using the geometry of a space, we can improve the accuracy on how we measure distances between covariance operators. Okay, so now how we generalize this to our more complicated setting? Essentially, we need to change the test statistics. Instead of using as test statistics the difference between covariance operators, we look at the dispersion of the covariance operators with respect to some barycenter. And how we define this barycenter? Well, in a coherent way with respect to the distance that we are going to use in meta statistics. So if and so we use a Frechet mean, which we look for a barycenter that minimize the square distance that we chose. So in simple case, the square root distance, this barycenter is obtained again with a strategy of mapping everything into the square root space and then take the linear average there and then go back to in the original space using a square transformation. Progressive distance, it's a bit more complicated. You need there is no analytical solution, so you need to solve that with an algorithm. However, it works pretty well in practice. Still, the idea is looking for a barycenter and then use test statistics, the variability with respect to this barycenter. Once you've done that, you can replicate the strategy of a permutation test. So you permute the label now instead of across two groups, across the multiple groups, so across the 5 languages. And each time you compute this test statistics and you build up the permutational distribution of your test statistics, which you use to compute the p-value. Okay, so what's the result of this? For the frequency covariance operator, we first apply the test individually on each language to look to test the hypothesis: is the covariance the same across the words or is different? As you can see from this p-value, there is no evidence that there are different covariances between the different words. And then we test between the languages, say, are the covariance between the different languages the same or are they different? And the very small p-values tell us that there is strong evidence that there are differences between languages. Now, someone can say, okay, but this is just an effect of your sample size because you have a larger sample size when you are comparing languages. It may be. However, this, as a minimum, this is telling us that with this sample size, which is the usual for these problems, there is no hope in modeling the individual word covariance structure. However, it's important to model the language-specific covariance structure that contains relevant information. Okay, so this was for the frequency. Similar result, same story for the time covariances component. I will not add anything on that. So the same strategy can be used for the mean. Just you use a linear distance between the means. And these are the results. So slightly surprising. For some languages, we have not enough evidence to say that there is difference across the mean, although, again, this is probably just the fact that the sample size is not large enough. However, for some languages, there is strong evidence of difference between the mean, so we need to model that. Okay, so I will leave to John to talk about how actually we use the model that we have defined.
Going back to what John was talking about right at the beginning, what the aim of this is to try and work out how we actually think about time change within the language family, and really try to understand what it means for a speaker of French and a speaker of Portuguese to be related through a sound change. So this diagram here really kind of tries to break down what we want to think of when we think of a particular speaker saying a particular word. So if we look first of all at the top line, on the far side we see that we have the French speaker actually saying the word themselves, and that can be broken down into a sum of the average sound of a French speaker saying the word one, any French speaker, plus some individual speaker-specific residual, which is then changed by the underlying covariance structure within the language, be it the frequency covariance structure or the time covariance structure. And because of this separable assumption, we can take those two bits separately. Now, what we would like to say is, what does it mean for a particular speaker to then be a speaker not of French, but say of Portuguese? Well, you now reverse the process. So the only part of the top line that is specific to that individual speaker is the residual part. So if we move that residual from French to Portuguese, but then now look at that in terms of the Portuguese frequency structure and the Portuguese time covariance structure, use that to alter the residual and then add back to the average sound for the group of people speaking Portuguese, that would give us a projection of that individual French speaker speaking Portuguese, because it would just come through the system. Now, that's the sort of first idea about how you might think about a speaker going from one language to another. Now, that's a very direct thing. We're saying take the French speaker and turn them into a Portuguese speaker. But in essence, actually, what we really care about is the time, the movement through that. One technical thing that we should think of immediately, though, is that if you think about this, of course, we're dealing with functional data, and so therefore the concept of the speaker-specific residual isn't really particularly well defined. However, we are going to look at, if you think about it in terms of finite sample truncated operators with a finite number of eigenvalues, you can sort of get around this. And of course, we never actually really utilize that individual residual. We only actually utilize it in terms of its being reused with a particular covariance. So in some sense, even if you don't like this particular way of doing it, they're going to the ill-conditionedness will come back out again when you remultiply, re-smooth it, if you like, by the underlying covariance structure of the other language. So we can do this in a formal way through truncation, or we can think about it in its full terms. But what we really then care about is how we actually go not from a speaker saying French to a speaker saying Portuguese, but the continuum between French and Portuguese. That's what language change is about. It's about a smooth change, a smooth continuum over time. So if we think about it now, instead of doing a direct substitution, what we'd like to do is create paths between each of these objects that are not the individual speaker, so that we can then map that individual speaker to anywhere along that path. So we can map linearly the mean path, because that's a simple linear spectrogram that we can then move linearly across. But as Davide was saying, it's really important that we take into account the geometry of the covariance operators. These are not objects that live in linear spaces, so therefore we need to take into account the nonlinear space that we must go through. And therefore we can use one of the distances that he used in the permutation test in order to define the path that we would like to take within those covariance operators, and then define that path for the frequency covariance operator. So define a path that goes through from the French covariance operator to the Portuguese one, and similarly for the frequency and similarly for the time. And in order to do that, then you can map any point along that path and see the continuum of the sound change. So how do we do that formally? Well, as I've said, you just take a linear mean interpolation between the language 1 and language 2 along some path where x can be between 0 and 1 to do a linear interpolation between language 1 and language 2, between French and Portuguese. If you so wanted, you could then extrapolate further and go past Portuguese and say, what does the sort of sound change look like if you go further away on the same trajectory as you had from French to Portuguese? In the case of the covariance operators, it's a little more complicated because you have to take into account this geometry. So in actual fact, we use the Procrustes distance that Davide talked about. That gives you a path in the Procrustes space. You have to do your minimization. You have to pick a particular unitary operator to then put within your interpolation. You do that interpolation in the correct space, in this L space, and then you take the function of the L and its adjoint in order to regenerate the covariance operator for each one of the frequency and time, and then you take the separable approximation to put it back together. So that takes into account the geometry, takes into account the underlying sort of square rootness of the covariance in order to then do your interpolation so that you're back within the right geometry to give you the complete covariance path that you need. And of course, again, because x can be anything between 0 and 1 or either plus or minus, outside that range, it gives you a way of either interpolating or extrapolating outside that range. So this is what it looks like in pictures. You have the mean covariance down the middle. The mean sound down the middle. That's the actual sound of the population changing smoothly. And then around the outside, you can see the smooth path in the correct geometry, the Procrustes geometry of either the frequency covariance operator or the time covariance operator. And then that allows you to put them together to give you the output from going from either French, say here in this case from French to Italian. Now, ideally, we would now be able to play you the sounds. This first example is going to be going from the number 5 in French to the same speaker, so using that same speaker residual, to the number 5 in Portuguese. Okay, so this should give you a... Okay, so this is a smooth path. It's got 10.
Yep.
10 So by the end, you hear it's going from cinq to cinco. And if you do it for 7? So that gives you the path for an individual speaker saying set to set. So that sounds okay, but in some sense what we'd really like is a little bit more structure. So one thing we thought about was, in actual fact, we know quite a lot about what speakers sound like in one language and quite a lot about what speakers sound at the other. So we'll do exactly the same thing, but now what we'll do is we'll take that endpoint and we'll look through our database of speakers and find the one that's closest to that residual true speaker. So this actually goes to your point now. What do you do? Well, what do you do is, instead of... he's managed to get it to go now. Okay, so now what we do is we use the closest residual. So now we define a path that says we take the first sound, the first speaker in one language, we take a different speaker that's close, the closest residual speaker in the other language, and then we plot a path between the two. And you see the path in that sense is much smoother. If you want to do the 7. Now, of course, all the intermediate ones are no one actually speaking. There's no intermediate speaker of those, and because they aren't really languages in that case. But the first one and the last one are true speakers of the language. So that gives us a way to generate paths that start to answer the question of how can you start to think about language movement between these historical languages. And it's the first step in being able to answer those questions about how do languages move around and how can you actually start to listen to different points within that evolutionary spectrum. And if you think about those trees, what you're suggesting is that you can go up and down those trees following a path that goes between these languages in a way that's smooth because of the structure of the covariances.
Final few words to wrap up everything. I hope we show you that there are some good opportunities in using functional data analysis techniques to analyze speech data. I would like to highlight that what put this work in a different position with respect to existing speech analysis techniques is that we are looking at the population of speakers, so we are not focusing on an individual speech track, but looking how the speech varies within each population, within each language, across different words, etc. And this is, I think, is really the really challenging aspect to do. So I hope that we show that there is the opportunity to do some good work in this area. And I hope we also convinced you that some of the hypotheses and assumptions we are making to work with this data are at least reasonable, at least looking at this pilot data set. So now, of course, there are a few open questions. So first of all, some of the statistical properties of these changing paths are still needs to be explored in more detail, but also the big question is how this generalized to larger dictionaries and broader set of languages, because to be honest, we focused on a small subset of languages that are relatively similar to each other, so how this generalized to move from one branch to another of the large trees. And also there is a technical point about the sound reconstruction. So we, at the very beginning, we disregard the phase because we said, and it's true, that there is no linguistic information to be explored there. However, when you reconstruct the sounds, you need a phase information, and it cannot be whatever. It needs to be something that is coherent with a sound, with a speech sound. So somehow we may, to make everything consistent, we may want to repeat the analysis on the phase as well. However, that's a challenging problem because the phase is an even more complicated object. It's not smooth at all, and so completely different approaches are needed there. So that's another big direction that is still open. Okay, so thank you very much for your attention.
This is a huge tradition of statistics in linguistics. I mean, one example is Rodney Yule and his book on distribution of vocabulary frequency distributions. George Siff, that you probably know, the rank frequency law in 49. William Lab of statistics and linguistics, and there's a lot of developments there still going on. And of course, more recently, well, there's a huge increase in linguistics and statistical analysis, or statistical analysis in linguistics, particularly centered about text. As John explained, that's not the issue with the paper we have just heard, but there's a lot about large speech synthesis or natural language processing, mostly based, I must say, in texts. And of course, there's a niche, I think, in which this paper fits very well. And if you haven't heard, or seen rather, the Ancient Sounds project webpage is very good. I recommend it, and it's many, many things that have been discussed here, plus other interesting aspects of the project. Well, this is a rather touching citation from the Mexican poet Octavio Paz. I have to make a disclaimer here. I'm Mexican, I'm bilingual, I have been in this country 30 years, and I still can't distinguish between D-U-G and D-O-G. For me, dog is the same. After 30 years here, I'm afraid I can't do it. So I wonder if at some point they would make me sound in English. But anyway, Paz says something very interesting about language. I think it's a very deep thing there. I very much relate to that. You know, I'm a citizen of the Spanish language. It doesn't matter where I come from. There's a language that identifies me. And interestingly enough, some people call it Castilian or Spanish or whatever. But I know what my language is, and that gives me an identity. There's, of course, a lot written about that. So I like that quotation. It sets the language scene. Language matters. And language and statistics matter even more. And that's why I enjoyed so much this paper. Well, sorry. Very quickly, we have heard about the aims of the paper, so I'll go very quickly on this. Basically, you have frequency, you have time, you have the spectrum, and the points about the phonetic transformation to more than one sound and map it into another language and come back, I think is very, very interesting. And I'll go back to that crucial point of the paper in a moment, of course. Something I would like to pick up is the interpolation and extrapolation processes that you can do using the methods we have been seeing in the paper. The interpolation part has been just very ably described by John Aston in this case. It's a smooth path between two languages. And I have a question at this point. I mean, we looked at the process between French and Portuguese, but of course the word for, just struck me when I saw that slide, John. The word for 5 in Spanish is the same as Portuguese, and I wonder how it would sound if you move from French to Spanish or French to Portuguese. Can you borrow strength to say this is a different language, although the word is the same? What would happen with the covariances? I don't know. But that would be interesting to see that process too. And of course, the other thing that the paper only touches very quickly is extrapolation process, which is when you put on top of this anthropological, genetic, historical information and move in the direction outside those smooth paths to try to reconstruct how language sounded 400, 500, and 100 years ago. I think that's a very interesting aspect of the project. And I should say, of course, the paper we have just heard touches it's just an iceberg. It's a very solid iceberg, but there's a lot below what we have seen and a lot of possibilities that are still to be explored. And again, I direct you to the website of the project. Well, I have quite a few questions about that. is there a discrete effect on the frequency domain? Some of the log spectrograms seem to have sort of ridges around. And I wonder if that's due to the frequency in which the samples were taken, 16 kilohertz. I wonder if you could, if you could even expand the range from 160 to something else and avoid that discretization problem. I mean, it's very easy to say that. I'm sure the computations are horrendous, but it's just a question. Other things is, of course, there's a very small corpus, 10 words, only no names. I mean, one thing that immediately springs to mind is Swadesh's 100 words list in Indo-European, or the 200 list. And of course, you are just working in the Romance family, so it makes sense to do it. What would happen if you look at English, Germanic family, and Spanish, in my case, Romance language? How would that translate? Of course, you would have less information. You have less cognate words between English and Spanish that you have between Italian and Spanish. So how is that going to affect? And how are the assumptions, the second-order assumptions, are they going to hold enough to move between different branches of Indo-European? I don't know. I loved the permutation test. I think that was a brilliant application of a classic test in a very complex situation. I really like that. However, of course, as the authors recognize, there are power issues. There's very few speakers, so to speak, and how can they be accounted for? Can we just increase the power for those tests? I think the conclusion is slightly unclear about what would happen if you had more speakers in terms of the power of the permutation test. I think the idea is lovely. I really, really liked the execution of it. Well, going back to my language, as you can see, there's a division between people who call their own language Castilian and some people use Spanish. I would use Spanish, I'm Mexican. I'm very interested in what happens with Uruguay and Argentina and Paraguay. I mean, in Uruguay they say Español, Spanish. Why would they say that so isolated? I don't know, but it might be interesting to map this very simple distinction in terms of how the covariances and the means sound. Well, of course, computation is very, very hard to do all these things. Again, how easy would it be to generalize these methods and use them in settings where you have very, very large data sets? I'm thinking in terms of accelerometry, which is becoming more and more prevalent, and you can sample every 15 seconds or even less during 2 weeks, 12,000 people. Can you think in terms of the methods for the spectrograms in such a big things? And of course, Fitbits, we know, are becoming more and more common in health studies. Can we apply these things to Fitbits in real time? I don't know how difficult computations would be to do things like that. The other thing, as I mentioned a moment ago, this is a very, very deep iceberg. That's my impression of the paper and of the project. How close are you to actually reconstruct how Indo-European sounded, or indeed how Shakespeare spoke, or how Cervantes spoke in the 17th century? I think that's a fascinating question, and I look forward to hearing about that. So my pleasure to propose a vote of thanks. Thanks very much.
Okay, before I start, can I introduce myself? I'm not a statistician. I actually did used to teach statistics at an undergraduate level at UEA for a couple of years, but pretty basic stuff. But I've spent my career in speech science and speech technology, and so my brief was to look at the speech side of things. I'd just like to say that I'm sure you must have noticed in the past years that the kind of apps and stuff you can get on your phone in speech now are really pretty impressive, and I say this as someone who's worked in the field. Speech recognition has really come on, as has speech synthesis. It's really good. And it seems to me that the authors haven't really engaged very much with any of that literature, which I think is a shame. And in the slides, I'm going to make some comments on some of the things they've said and some of the assertions, and also point out some of the things that I think are probably not the way we would do it in speech science and speech technology. So the first thing, I was very interested in the paper. It looked really exciting, and especially when they said that they were going to have multiple speakers. But I was very disappointed to see the very small size of the data set. And something that's been happening in the speech science world since the 2000s is the data sets have been growing larger and larger and larger. And the difference between speakers is a real nuisance. It's a nuisance in speech recognition. We've just about conquered it now, I think. And we typically use hundreds of speakers with hundreds of hours of speech for our experiments. So this, about 145 seconds, is a very, very small data set. And I just wanted to gently point out that there's a lot of data out there that you could use, ELRA, this resource here, where you can get, not for free, I mean, it's not very expensive, a lot more data to use. Perhaps you're going to do that in the future. So here's a comment about the extension, because I was slightly worried about the premise. So it does seem to rely on the fact that the words, I mean, you've chosen the digits in these 5 different languages, and of course I looked them up because I'm not a linguist. They're very, very similar. But how would it extend? How do you know if a word is sufficiently similar to its counterpart word in another language to be able to use that word? So would it work for the digits in English and German? They're fairly close. What about English and Russian? No, some of them are the same, but some of them seem to come from quite different sources. Another slight problem is it relies on using isolated words. Well, most of the speech data we've got is continuous speech. So I think what you should be thinking of doing is extending it to continuously spoken speech. So this was really my problem right through the paper, the size of this data set. And it seemed to me that the variability between the languages is very small. I mean, you might, for someone who's not a linguist or a Spanish or an Italian speaker, they might even have difficulty identifying which language is spoken, but they could probably pick out the speakers quite easily. And this is well-known stuff in speech science. Physiological variations, so the difference between a small child speaking, they've got a small vocal tract, so the resonant frequencies of their vocal tract are much higher than a tall man. So you get a lot of acoustic variation in speakers. You also get accents as well, and you might have been very unlucky, and maybe all your Portuguese speakers had Spanish accents or something like that, because you only had 3 Portuguese speakers. So I think this is a problem for the work. Okay, so sorry, I'm going to preach at you a bit now, but I need to point out that a lot of this stuff is already current. So you say there's, sort of possibility of mapping from one language to another. People have been looking at that for a long, long time. There's been quite a lot of an awful lot of work. There are working systems out there now which will take an English speaker. I don't speak any Mandarin, but they will take me and make me speak Mandarin to a high standard. It's there in the speech world. So you need to look at things like the IEEE transactions on audio, speech and language, or the proceedings of interspeech or something like that. And here's another one. You say, oh, it'd be exciting, we could make a synthesizer speak like any person. Again, it's been hugely researched. There was a thing in 2016, the Voice Conversion Challenge. There were 17 international groups involved. They got data from a source speaker and a target speaker, and the goal is to turn the voice of the source speaker into the target speaker. And it's all very professionally measured. They have mean opinion scores, they have a panel voting, they do statistical significance tests on the results, all that kind of thing. And it's that, it's that kind of approach that's enabled these applications to work. There's even a website now where you can, I tried it wasn't very good actually, but you can put in 1 minute of audio, so you can put in 1 minute of Donald Trump or something, and then you can make Donald Trump say anything you like. Actually, he does that anyway, so it doesn't matter really. Okay, now here is another major problem, the provenance of the data. It seems to me you don't know where this data's come from. You don't know how it was recorded. Now, it seems likely, the usual thing is that, say, all the Italian recordings were made in the same place with the same microphone and the same setup, all the French recordings were made in the same place, but all those places would have been different. So, in other words, there's a complete correlation of the languages with the recording channels. Now, that is a problem, and for instance, speaker verification, where someone says, I'm Stephen Cox, and it takes my voice and it verifies it, they've spent a lot of time deconvolving the effects of the channel from the voice. It's not a trivial problem. So there is a real problem here. What you might have been actually looking at was nothing to do with language. It might just have been recording channels, different recording channels. Okay, I don't think the analysis was right either. So you had a spectrogram and you discretized that. Well, they are discrete when you compute them on a computer, of course. So you had 81 frequency points from DC to 8,000 hertz. That's fine, but it's not fine just to use those points for a simple reason. Your frequency resolution is about 100 hertz, right? The ear hears logarithmically, okay? So there's a piano keyboard. I'm trying to show that. You can see there I've got A 110 hertz. The next A above that is 220 hertz. So down in that part of the frequency spectrum, 100 hertz, which is one of your points, spans nearly an octave. It's like putting your hand on an octave of the piano. But when you get up to the top, the piano doesn't go that far, actually, so I had to move it up a bit. At 7,000 hertz, 100 hertz is only a quarter of a semitone, right? It's less than half the distance between a white note and a black note. So, in other words, the points carry less and less information as you go up the frequency range. So that's one problem. The other problem, if you use the spectrogram, I don't know if you looked at the spectrograms much, but the most energetic part of any spectrogram is the pitch signal, right? That's the lowest part of the signal. That corresponds to your vocal cords vibrating, and for men it's about 80 to 120 hertz. For women it's a bit higher than that. That's where most of the energy in the spectrogram is. It's not a good idea to include that. It's highly speaker dependent. You don't want speaker dependence in this. You want to get rid of it as much as possible. And there's no information about the identity of the word in the pitch. Now, there is a basic technique, which, well, it's not basic, but we have been using it for a very long time, something called Mel frequency textual coefficients, where you get over the frequency resolution problem by having bands which are very low bandwidth at low frequency, and they get higher and higher as they go to high frequency. And there's some tricks that you play with using a cosine transform and then taking the lower half of the coefficients to get rid of the pitch signal. And you can go back from the MFCCs to a time waveform. It's possible. Okay, so now let's get on to the paper. I mean, I thought the stats was really interesting. I don't claim to understand it all, but this was my feeling about it anyway. So this thing about the means. So you took the means of the words in each language, and you took the p-value, the significance of the difference. And when you look at it, the p-value really just does seem to be correlated with the number of speakers you had. There's some correlation. The highest p-value is for French, where you have 7 speakers, and the lowest p-value, well, also American Spanish, 5 speakers, but the lowest is for Portuguese, where you've only got 3 speakers. So it's kind of implying to me there simply wasn't enough data there to do that test. And the covariance, again, I thought, I mean, perhaps you'll correct me because your understanding of this, of the statistics is more sophisticated, but what I saw there was there just wasn't enough data to say whether the covariance was different. But my feeling is the covariance probably simply reflects the fact that all the words in a particular language group are uttered by the same set of speakers, That's the main effect, and they were all recorded. We're coming back to the channel effect. They were all recorded under the same conditions. So there's a lot of homogeneity there in the words from one language. And because of that, I don't think there's any reason to expect they'd be different. But I don't think it's anything to do with language. That's my feeling. So this brings me on to the next point. I think it's more likely the covariances are simply a reflection of the different speaker populations and the recording conditions. And I got so interested in this, and I've got time on my hands, I had a go myself. So let me show you what I did. I've got some recordings of English speakers saying the digits which I used. And so I took two groups. I took one group of 6 and a second group of 6. Now these are recorded under the same conditions, so there's no different channel effects there. And I think I basically implemented your technique. I used dynamic time warping, as we call it, dynamic programming, to align the utterances of the same word. I took the means, I took the covariance of the residuals of the means, and I got, it hasn't come out very well on here, but I got something like that. So that's group 1 and that's group 2. Of course, now, I mean, we're faced with the problem of saying whether they are different or not. I think they are probably rather different, and to me, that just means that they're two different groups of speakers said these words, and the covariance is a reflection of the resonances in the vocal tracks of those 6 different speakers. That's my feeling. But just going back to this, it's a very interesting assertion about this covariance thing. Does it work if you increase the number of speakers to hundreds rather than 3 or 5 or 6, however many you had? Do you still find that the language covariances are still different? Because I would say they would converge to a single covariance matrix, because it's nothing to do with language, it's to do with just resonances of vocal tracks, a lot of resonances. But you could use them as in a language identification experiment. Now that would be interesting. Can you use the covariances and identify a language? Okay. Moving from one language to another, I was a little bit skeptical about this as well. In fact, you did use 2 techniques, didn't you? There was the simple technique where you just moved in the log-spectrogram place, but there was the technique where you compensated using the covariance operators, and that would seem to me much the right thing to do. I think there are all sorts of problems just moving in the log spectrum space. One thing is, if you just move in a frequency space, you might traverse spectrograms, intermediate representations, that there's no guarantee those could have been produced by a human. So the kind of thing that's been done in our world, we use something called hidden Markov model speech synthesis, and you move in a space where the Markov model states represent viable speech utterances. That's something you would need to look at. Okay, so sorry, this is a bit arrogant of me. I'm going to say the way I think you might go, but I do think you should get some bigger databases. It's very interesting, but until you've done it on some larger databases without this terrible possible issue of recording channels, I think you can't say much. Maybe look again at the feature extraction techniques. I'm not sure. It's a very interesting premise about the frequency covariance. I'm skeptical, but I would be very interested to be proved wrong by that. But I think the main thing is I really think you should submit this to a speech science journal, because it is really speech science. The statistics is of great interest here in the Royal Statistical Society, but the application would be of even greater interest to the speech community. So that's my recommendation. Okay, I'm sorry if that was hard. Okay, thanks.
I'm Bernard Silverman. I have no particular affiliation because it will take me more than 5 minutes to give them all. First of all, just in response to the previous speaker, if that wasn't statistics, we have a real problem. And the idea that you have to submit a paper to a speech science journal is a real condemnation of the Royal Statistical Society, because what the previous speaker has been talking about is absolutely statistics, and he's been doing statistics all his life. So we welcome you to the place that unfortunately you don't feel is home, but it is. The other thing is that it's very much in the tradition of the RSS that the seconder does exactly what you did, so thank you, that was fantastic. The next thing is it's fantastic to see functional data analysis, and both what the seconder wanted and what the speakers were talking about in the paper is functional data analysis. It's the idea of thinking in depth about data of this very complex form, and it's, to me, a fantastic thing that functional data analysis rears its head here, and I'm already credited in the paper. So some points. First of all, the seconder talked about resonances in the vocal system, and that suggests using some other basis than just local Fourier transform, but trying to get to the eigenfunctions or the resonances and use those as a basis rather than just using Fourier transforms, because there are many different ways of cutting up time, frequency, space, many eigenfunctions you can use, and maybe that would give something interesting. There's a lot in the paper about smooth changes between languages, but my understanding of linguistics is that there are not smooth changes between languages, and there was a thing called the Great Vowel Shift or the Great Sound Shift, and in my own lifetime there has been a real change in the way English has been spoken. And when I was young, there were lots of people around who spoke with what we called Edwardian accents, and only the Queen probably still speaks that way. And if I may say, I met her grandson the other day, as some of you may know, and he doesn't speak like that. He speaks more like I do, and that was quite interesting. So, there's sound shifts really happen quickly, and the way that we speak now is quite different from the way that people spoke 40 years ago. And so there is a thing to look at. Another interesting thing you could do, even in this room, is to get native speakers of one language speaking another. We've had about 6 already. Great. They all speak a lingua franca called English. But, you could ask Mario and Davide and Pantelis themselves and see if their covariances, when they're speaking English, actually match Mexican Spanish or Greek or whatever it is. So that would be an interesting thing to do. Now, table 2, if I may just say, demonstrates something that needs explaining, which is when your p-value is very big, as Gregor Mendel discovered, or we discovered about Gregor Mendel, there's a real problem when your p-values are 0.99 and 0.97 and 0.98, because they suggest the hypothesis fits the data too closely, and that's something that I feel has to be explained. Please do it in your response, whether or not I remember to put it in my written comments. And then finally, I'll echo something I wrote down before the seconder, which is if there are obviously very large databases of people speaking different languages, and you can switch on the radio, we can get them on the internet, and you can just, and so do those confirm the covariance hypothesis? Do those confirm the idea that there is a language-specific covariance? Because there's no doubt that when you listen, if you're used to listening to languages, you can sort of hear what language it is, even if you haven't the faintest idea what's being spoken. So there is something about languages that's different between them. But what is it? Thanks for a really stimulating talk. Thanks for a really interesting piece of work. And I really apologize. I'm doing the terrible thing, which is to make my comments and then run away. But thank you all. Thank you.
First of all, congratulations to the authors on an outstanding contribution for analysis of acoustic phonetic data. This work has actually provided a foundation for much of my own research, which is an interdisciplinary project. There's a partnership with the Centre for Biodiversity and Environment Science at UCL. And I'm going to try and discuss a little bit more the broader applications of this work in particular with relation to phylogenetic Gaussian processes. So a major theme of this paper has been the reconstruction of ancient languages based on sound recordings of modern languages. And so if we want to do that, given our data, if we want to do that, we need some modern speakers, so some data, and we will also need a phylogeny, which is denotes the evolutionary relationships between speakers. Now, if we adjust the author's notation so that P will denote the position of language L on a phylogeny, we can actually model these spectrogram surfaces as phylogenetic Gaussian processes. So to do that, we make some assumptions. We assume that descendants are independent given their most recent common ancestor. We assume also that the Gaussian process is independent of the particular topology of the phylogeny. And we also assume that the covariance structure is separable in the phylogeny space and the spectrogram space. And with these assumptions in place, we can say that the spectrograms are a linear combination of some mean function and fixed basis functions. And the weights of these basis functions can be driven by our GPs. So we look here, we can see the ZQ. That's just a noise process that can be thought of as driving within language variation. The FQ here is a phylogenetic GP, which is univariate and independent for each of the basis functions. And this is typically modeled by an Ornstein-Uhlenbeck process. This is a standard process that's used for modeling in evolutionary studies. So this model could be used to model the pronunciation of the digit 1 in Latin, as was spoken by the Romans. But there's a lot more to modeling and reconstructing language than just the digit 1. So what I want to talk about is how this model maps directly into a very different research question, which is the evolution of echolocation calls in bats. And so here, what I've shown you is a set of bases, phi 1, 2, and 3. And these can be thought of as the evolutionary bases. And these can be derived from the data by a PCA or an ICA. Then, if you look here, we can see the characteristic mean spectrograms for 4 different species of bat. And given the basis, we can decompose those and find the weights of each basis for each species. We assume that the bases are modeled according to our phylogenetic GP, and this allows us to create a posterior distribution for those weights on the ancestral nodes. Taking map estimates for these ancestral weights, we can actually reconstruct ancestral spectrograms. So just as you might go about reconstructing the digit 1 in Latin, the same model can reconstruct the echolocation call for bats that lived 20 million years ago. So there's a number of questions outstanding here. Can data like this actually be used to effectively infer phylogenies? In the case of language, I don't think this is necessarily straightforward. There's a number of questions that I would have. What is the important characteristic to model for language? Do we look at it on a word-by-word basis? Would you instead look at the covariance structures, which have been talked about quite a bit? How would they cope with this geodesic interpolation in our models? Or perhaps is the case that we can actually find a set of basis sounds and model the evolution of these. Finally, on a slightly different note, I was quite interested as well in the permutation test procedure. And I found myself wondering as I was working through it, would it be possible to transform this test statistic in such a way as to give a pivotal quantity? And in this way, then, you could look at more powerful, strong controls of family-wise error rate. I don't expect any of these questions to be answered immediately, but hopefully they've provided some interesting food for thought. Thank you.
I really appreciate the work the authors have done, and I'm collaborating with them, so I'm somehow giving myself a compliment here. But I have a couple of comments. The first one has been said by the commenter, is that when you have a sound wave, there's no laser, okay. So when you have a sound wave and you work with the spectrogram, in the top rows of the spectrogram, the high frequencies, between different speakers you have misalignments. So if you then take averages, you smear out these peaks and the sound reconstruction is not very good. Whereas if you work with something called the male frequency capsule coefficient, which is given by taking the spectrogram. You take band averages of the spectrogram, and then you take another Fourier transform. This is what you see in the bottom right, and then you have less problem with the frequency misalignments, and also you can get quite good quality sound reconstructions, not necessarily with this version of the MFCC, but with different versions of the MFCC. Okay, so the advantages of the MFCC are what? Well, the principal ones is that it provides you a dimension reduction. Here on the bottom right, you have 10 frequency channels or Q frequencies if you want, whereas in the top you have much more. And also it's robust to small frequency misalignments. The price to pay for that is that it's quite difficult to interpret because you have this double Fourier transform. Okay, good. Small note on the registration. Registration of time one-dimensional curves is something that is quite easy in the sense that the discrepancy that you take, you can just take an L2 metric. For two-dimensional objects, it's not clear what metric you should take. L2 is one thing to take, but you could want to use a weighted L2 or look at something completely different, which is, for instance, relative volume. So that's it. And the final thing is, I just came back from 3 weeks in Thailand, so I had 3 weeks to think about, does the covariance of Thai, is it really something that distinguishes the Thai language from English or French? And I came to the following conclusion. You have two things. You have the within spoken word covariance, and when I take covariance, I don't mean exactly covariance, I just mean patterns of variation. And this allows you to do what? It allows you to distinguish between the sound of a word and the sound of another word. And this is different for different languages. So in Chinese, you have the different versions of ma, two of them being ma and ma. And to an English speaker, they would sound the same, but to a Chinese speaker, they sound completely different. And underlying this is that the Chinese speakers, they've developed a sense of the covariation that is different from that of an English speaker. But so within spoken word covariance or variation allows you to distinguish between words, but I believe that what really makes a language sound different to another language is the covariance between the words. Okay, so you take spoken words, you take the average word sounds, and then you look at the covariance between these. And this gives you a sense of how different, how a language can sound, and perhaps you can generate sounds of things that are not words, but sound like a certain language. So when you speak gibberish, you can say that this gibberish sounds like English or sounds like French, but it doesn't mean anything. So that's what will come. So yeah, so to summarize, there is this within word covariances, and that's what the paper is talking about. And that's something interesting because it allows you really to distinguish between the different words in the same language. But you have this, I think, between word covariance that is also very interesting. And I'm not a linguist, I'm not a phonetician, but I just thought that if I had to give my best guess, that would be also something interesting. A final thing I wanted to talk about, some notation, technical notation for tensor products of operators, but I'll put this in the written discussion. Okay, thank you.
I've certainly found it fascinating. Sorry, Jane Hutton, University of Warwick. I found it fascinating to listen to this and to do what Shaheen did, which is to think about what's happening in this. I guess one of the questions I would ask is which approach, the kind of approach that Stephen Cox was talking about, or the other approaches would be best for, in the forensic case, when you really want to know who spoke and, you know, probably very, very quickly want to know whether this is plausibly a terrorist or not. So I'll just leave it as an open question.
I'm Jeff Nichols from the University of Oxford. Thanks very much for the talk, very interesting. One thing I was thinking about was the time registration. So you only rescale on the time axis, not on the frequency axis. Suppose you were to rescale on the time and frequency axis, but only use the transformation on the time axis. it seems to me you might be tricked by some structure in words, and you wouldn't be tricked if you did it that way. It's just a simple thing. I guess the question of working with homologous classes of words and also with short words, I assume they're all kind of short words, one or at most two syllables. And so the previous speaker talking about covariance structure between words, I suppose also for long words, sort of four-syllable words, there might be a similar story. And then the last thing is I'm quite interested in phylogenetics myself, and I can see there's a certain sense that it seems a little bit hopeless that these would actually be physical if you kind of map this onto a tree with some kind of straightforward scheme. But on the other hand, it might not be so hopeless if somehow you took first of all, if you took many leaves, then you'd get strength. I think one of the previous speakers has referred to this. You get strength from the requirement that you satisfy many constraints at the interior nodes coming from the different leaves. But also perhaps if it were possible to consider family trees that were over relatively small timescales, perhaps not necessarily between languages, but between, say, dialects within languages or something like that. So that's me.
First of all, thank you very much to everybody for a very thoughtful contribution and comments. For sure, this was the beginning of the larger project for us. So we are very thankful also for pointing us to connection to different fields, which can be helpful for us. So I will leave John respond later on the database structure and the more phonetics aspects of the project. So I would like first to, first of all, yes, larger data sets with broader words, as we mentioned before, for certain would be helpful. And thanks for pointing us to existing sources which we can use in the future. However, I want to also to stress that we are coming from a slightly different perspective with respect to the language process, speech process, which is that the speaker is not a nuisance for us. We are interested in looking at the population, at the variability of the population. So in that sense, even if there are some techniques that already answer some of the immediate problems, we maybe want to work on something different because of the final goal is different. So I was thinking in particular to the voice challenge transformation. So, well, first of all, that's kind of the opposite of what we are doing. But apart from that, even if the techniques works, we are looking at understanding the evolution of the language as a whole. And so what we are doing is, even if we suggest in the paper some possible byproducts, the main goal is still trying to understand language evolution. So in this direction, there are also a lot of interesting suggestions of things that we can do to improve over this basic smooth change. So including sharp changes, including a phylogenetic structure, and all of that is for sure a very interesting direction we should investigate in the future, building on this basic structure. So last thing I want to comment on is the permutation tests. Yeah, sure, the small sample size of the test for the words is an issue. We reported that essentially for transparency and completeness. We didn't really rely on that. But on the other hand, nobody noticed that the test in the other direction, so the test within languages reported a significant difference. So that means that actually in our data set, even if that small, we can actually saw a difference between what we call the languages. Now we can discuss that are artifact of the grouping selection, and we may investigate that better, but still that means that there are actual differences and not by any possible groups, because otherwise if any possible groups would give a significant difference, that would have caught by the permutation test in the labels, the permutation of the labels. So maybe I'll leave to the other authors to say something else.
Okay. Well, I think before we hand over to John on the sort of more linguistic aspects, I think that for me, the kind of thing that was interesting, and I think there is still a lot to do, and I think a number of people have said that, is the fact that it is a different way of thinking about it. I think that there are many other techniques of thinking about speech processing and language analysis, but I think the fact that we're concentrating on what the covariance does, and that is an object of interest, and I think it goes to what a number of speakers have said about how there seems to be an intrinsic thing that even if you don't understand the language, you can often pick up what the language is. Now, to me, that sounds like a variational issue, both sound and sounds. I think that there seems to be something inherent in there. So while absolutely it's a small sample size, I think that as an object, it does seem to be interesting. And because of the structure of that object, we do have to be a bit more careful with the statistics than we might well be if we just took linear analyses, which we can't do because of the covariances. But I think other than that, Davide's done an admirable job.
Thanks. Yeah, I'd just like to make a few clarifications and responses. This is not so much a single project as a collaboration of people at different institutions who've been doing a number of sort of more or less separate experiments on various aspects of the space of problems that we're in, which is what techniques do we need to better understand and better model the nature of variation between languages and in the historical dimension. And that's why this particular paper and the data set that's been used, a number of people have made reference to the fact that it's really quite a small data set, and it's absolutely legitimate. It is, in a way, like a pilot project. And in fact, all of the little experiments that the group as a whole have done, we've published other things elsewhere on other aspects of these problems, they do tend to work on small data sets. I absolutely take Steve's point about the possibility, in fact the normality in some other areas of speech work, of using much larger data sets. And of course, one would aspire to do that. But this, when you're trying to cut new turf, or at least what's new for oneself, even if others have gone further elsewhere, it makes sense to start with a smaller pilot. Now, some questions have been raised though about whether the size of the data set is large enough to get anything sensible about. I would like to try and allay one of the fears or concerns that Steve had about the possible confound between the channel and the languages, because I think we can put pay to that. It's not the case that each language was recorded by a well-defined, small group of people, each of whom in a common environment, nor for any single speaker it was necessarily a common environment. Of course, larger amounts of speech data are available in large corpora. I know that perfectly well and use that in other areas of my own research. But for this particular area of work, what we're doing is trying to recapitulate what's been done in classical scholarship in comparative philology, which tends to work on individual isolated words. In the textual analogy, what you have is the dictionary and comparisons between the dictionary. Off-the-shelf spoken material generally isn't like that. It's continuous speech, and that, of course, would be interesting, but it's going to be very challenging. So what we had to do is sort of mine our own or pull together our own cross-linguistic database, and continue to do that for many other languages beyond the small data set here for Romance. And that's why we turned to freely available off-the-shelf language. It tends to be a language teaching material and online dictionaries and that kind of resource where one can get reasonably clear recordings from a number of different speakers, or not large numbers of speakers, but from different speakers of words that are spoken in isolation. So that's the design considerations that went behind the way in which we worked, and which I hope will explain to some extent why this data set, admittedly, is indeed really quite small. But it's been quite useful for exploring various hypotheses and for running some tests. And there's, for sure, absolutely much more could be done. Several commentators have pointed out that working with Fourier domain spectrograms has its limitations. Absolutely, completely well aware of that in other experiments, in other papers, in other aspects of the work. We're having also worked with, when we first started working together, I was advocating, I'd been using linear prediction, representations of speech, and then, in fact, since 2015, I've been using MFCCs as the representations in the experiments that we've been using. Shaheen sort of picked up on that a bit too. Admittedly, the work that I've been doing using interpolation and modeling evolution using MFCCs hasn't had the population level statistical dimension that this talk represented. So there's still a bit of a disconnect between those two lines of work. In terms of actually making the simulations of how words can change as you move from one pronunciation to another, which could be one pronunciation in one language or versus another, or it could be one pronunciation at one period of time and a different pronunciation in the same language. In terms of those simulations, the tools and methods we've been using it doesn't seem to be sensitive to what type of, in practice, hasn't seemed to be sensitive to what sorts of representations you're using. So the perfectly legitimate concerns, for instance, that Steve expressed about how if you move through the space in a particular direction, will you go through a region of the space which isn't a possible humanly utterable thing? It's a perfectly reasonable concern, but it's not been, because it's not been realized, we haven't worried about it. And I guess perhaps we've been therefore drawn into a complacency about that, actually we've been amazed at how well it does work when you compute a path from one pronunciation to another. In fact, in some cases of simulations that we've built in that way, in an attempt to model actual process of evolution, we found that intermediate stages in the evolution are right. They're proper for the historical record. So one example of that is one of the reasons why we were comparing Portuguese with French is that modern French is thought to have derived from an old French pronunciation which was like modern Portuguese. We're not saying that French derived from Portuguese. We know that's not the case. But the pronunciation of modern French for that word derived from something which was more like modern Portuguese. In going from to you go through an intermediate stage which sounds more like and that is a more conservative French pronunciation. So by modeling the trajectory from A to B, go through point C and point C, D, and so on. And sometimes those immediate points seem to be right. They seem to fit with the conventional textbook story about how these languages evolve, which gives us confidence that we must be doing something right. For other simulations that we've run, I haven't spoken, it doesn't work. We get intermediate pronunciations which are perfectly plausible, humanly utterable pronunciations, but they do not reflect the right history. The actual history went through some other way. So one example would be the derivation of trois in modern French from Latin tres. The simulation and you move from tres to trois does not go through an intermediate point, which is what is believed to have happened, which was something like trois. The spelling T-R-O-I-S of modern French is thought to reflect an older pronunciation, something like trois. But if you do a linear interpolation from tres to trois, you do not get a trois. So in that case, the interpolation path doesn't go through the right region of the space. So there's more. So the shape is not the trajectory is not a straight line. It's some other shape or some other geodesic. Now which is kind of, it would have been nice if it did work, and it didn't. So that's good science, because we tried something and we learned we were wrong, and it wasn't right. So and that's the fun of this kind of these experiments, is that sometimes it works out okay, sometimes not. And there are many possible and indeed probably better ways in which we could try out many of these things that would lead to to improvements in the future. And clearly this is still what we've described today. Is just a small portion of a large number of different fronts that we're pushing at, and hope to combine and actually hope to engage many other colleagues and students and so on to take up and do better than us, right? Or to pick it up and go with it and show us how to do it differently, or to be inspired whatever way people think would be a good way to go.